Hi, my name is Fayo, and I go to the University of Maryland, Baltimore County. I'm a computer science major.
My name is Tangie Beverly, and I attend to Liberty State University. I'm a computer science major and an upcoming junior.
So our project is called an integrated approach for software safety analysis. When I was thinking of a project to do when I came here, I knew that I wanted to do something that was human-centered, some sort of cyber-physical system that I knew was safety critical, and I wanted to think of all the safety software requirements for that. And that was how this project started.
So a brief introduction to our project is our research. Software safety analysis is noted based on an integrated model to be both functional and safety. In result, it does not give analysis for all possible failures. The objective of this research is to integrate safety analysis method with functional requirements to reduce failures and perform the two independently. We use the FTA, which is used to analyze causes of the hazards and create a UML state chart diagram. The state chart is the standard for representing the functional specification of the software system. My partner and I chose this case study to integrate the FTA in the state chart. Now, our research goals were to gather information on the state chart and the fault tree, next find a case study, and create a fault tree and a state chart diagram. So what is a fault tree analysis? FTA is one of the most widely used for methods in reliability and safety security. It is a procedure for determining any possible combination of causes which can lead to certain undesirable events or events. There are 3 tests of the FTA, and that is to generate a logical tree structure to understand the connections, identify any possible failure causes, and a combination, and lastly, the calculation. Overall, FTA has the capability of providing useful information concerning the likelihood of the failure. So the fault tree block types, as I mentioned before, is a fault tree and a diagram representation of the relationship between the lower level events that may be hardware failures, software failures, and a human error and system level undesirable event. The FTA is made up of levels that each event is generated from the lower levels with various logical operators known as gates. The symbols are used in the construction of the fault tree to represent the gates and events. These are some of the symbols described. So the state chart diagram, there are many names for the state chart diagram, such as the state chart and the state machine. It illustrates the states in a unified model language known as UML. A state chart is composed of states, events, and transitions. The state chart diagram describes the flow of the control from one state to another. And some of the keywords of the state chart diagram is the initial state, which is the state of an object before any transitions. The notation for the initial state is a small solid filled circle, and there can only be one initial state in the diagram. States are identified as the conditional objects when an event occurs, and events are the instant and the time that may important to the behavior of the object in the class. Transition is the moving from one state to another, and lastly, the final state is the end of the object existence. So the purpose of the state chart is to document all possible paths in an object. It can help identify important object attributes. Second, it can help refine the behavioral description of an object and to describe the different states of an object during its lifetime. So to design a state chart diagram, you have to think about the following points. You need to identify the objects, states, and the events. And this is a diagram of the state chart. The small black dot is the initial state, and then the boxes are the states, and the arrows pointing to the states are the transitions, and lastly is the final state with a small black dot down below. And next we get into our case study, the stair climbing wheelchair.
No time for any sleep when you by my side, and we're burning on through the night. You and I with one desire, playing with wildfire. We're burning on through the night. You and I with one desire, playing with wildfire. We're burning on through the night. Day comes again, repeat every step. With you by my side, I won't see an end. We're burning on through, we're burning on through the night. You and I with one desire, playing with wildfire. We're burning on through the night. You and I with one desire, playing with wildfire. We're burning on through the night. Here we go, here we go. Here we go, here we go. Here we go, here we go. Oh, 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 oh. Here we go, here we go. You and I with one desire, playing with wildfire. We're burning on through the night. You and I with one desire, playing with wildfire. We're burning on through the night.
So basically, that video just showed the case study we picked. We picked a stair climbing wheelchair that self-balances and climbs stairs backwards. When we were thinking of the safety requirements for that, we mostly focused on its design and how the way it's designed can, lead to safety errors. It's battery powered, so we were thinking of how, the battery could run out, how bad weather could wear and tear down the parts. So we used all that information to create the fault tree model that you see here. We made the top level event injury to user because this is a device that's supposed to be used to make the lives of the user much easier. So we think that one of the worst possible things that could happen with using this is injury to user. That could happen by one of two ways, which is incorrect usage and mechanical failure. Under incorrect usage, that could occur when the user is not paying attention to the limitations of the wheelchair. Some of the limitations of the wheelchair include certain step heights that the wheelchair cannot get over, or certain slopes that it will have a difficulty traversing over. And that's in combination with user error. On the mechanical failure side, that can happen in one of two ways, from damaged parts or inclement weather. Damaged parts can occur from strenuous use and poor maintenance. So these are the major things that we think can all contribute to injury to the user. This is the initial state machine that we came up with. It basically just illustrates the steps the wheelchair goes to when it's climbing up a staircase or going down a staircase. Obviously it starts at the bottom or the top of the staircase. Then it aligns to match where the stair is. Then the user sets the wheelchair to climbing mode. And that's when the process begins. The rubber tracks are lowered, they grip the stairs, and then the tracks are lifted up. All the while this is happening, the seat is balancing so the user cannot fall off. And then we modified that state chart and put some of the events that were in the fault tree into this state chart. And we put the slope limitation event as well as the rubber tracks wearing off, which we grouped in as damaged parts, as well as a damaged staircase. Because as you saw in the video, all the staircases that the user went over, they were all perfect, but it didn't show what could happen if there was a damaged stair or staircase. So we think that things could go wrong with that, and we think we did a great job of illustrating the functional requirements as well as some of the faults in this modified state chart. This project did not come without challenges, however. We wanted even more information to make an even more detailed state machine, but we had issues with communication. There were time restraints, and because of the issues with communication, we couldn't get all the information we needed to make the state chart and fault tree as detailed as possible. Those are just some of the issues that we encountered. In the future, we want to find better ways to integrate functional requirements and safety faults. And with more time and more details about a case study, we think that we can make it even better next time and possibly even make something that can be used on any system. And hopefully in the future, we'll be able to apply this to a larger, more complex system. In conclusion, there are ways to integrate functional requirements and safety requirements into one model. And by doing this, it makes it easier for companies to address safety requirements as quickly as possible. Usually a lot of companies, they do functional requirements in design while they do safety requirements during testing or even later than that, and that's really expensive. So by integrating them together and doing them at the same time, it leads to a much better result. And we just want to thank Dr. Wong for giving us the opportunity to conduct this research and the NSF for funding the research project. These are some of the references we used, and that's all.